Alright, this is going to be the second video that goes along with stuff that you learned since elementary school. It shouldn't be too difficult, but I might get into a little more of the physics behind the concept of why temperature changes as a function of what time of year it is, basically the seasons. Okay? First thing I want you to know is about something called the gyroscope or a gyroscopic effect. When things spin, when things rotate, they rotate about an axis, which you guys know is the north-south, the axis of the Earth's rotation. Now, when things spin, they become fairly stable around that axis, and the more massive something is, the more stable it is. It's called rotational inertia. So inertia is a resistance to change, right? It means it wants to keep doing what it's already doing. So if it has a lot of rotational inertia, it's going to stay pretty stable in that rotation. And the more mass you have, the more stable you are. The Earth is along the lines of 10 to the 24th kilograms. That's a lot of mass. It's a pretty stable rotation. So what that leads itself to is when the Earth rotates around its axis, as it goes through any given year, the axis that it rotates around, that again is the Earth's axis there, tilted 22.5 degrees, is going to stay constant as it orbits around the sun. Okay, I want you to remember that, which you all already know. You even know the name of the star that always happens to, total coincidence, be pointed towards. It's called the North Star, or called Polaris. Okay, now, there are going to be a lot of YouTube haters out there. They're going to say, well, V, you're lying to them because the Earth does kind of change a little bit, and that's true. When you get to a more advanced physics or astronomy class, they will teach you a little bit about something called precession. The phrase I use to describe precession is nothing lasts forever, kid. What that means is the star that we presently call the North Star, which is Polaris, wasn't always the North Star. And it ain't always going to be the North Star. In fact, it is getting less and less north as time goes by. So eventually, we won't call that the North Star anymore. We can't. It's not going to be in line with the northern axis of the Earth's rotation. Thousands of years ago, it was a star in the Big Dipper that happened to be the North Star. A couple thousand years, it'll be Vega that becomes the North Star. A couple thousand years. But again, we're talking long-term cycles here, okay? So, you know, if you're just in a class that wants to explain the differences in seasons here on planet Earth, they'll tell you the axis of the Earth doesn't change, okay? If you're in a much more advanced class and you want to study the evolution of the planet Earth over hundreds of thousands and into millions of years, then, you know, okay, you can talk about the Earth's axis changing, something called precession. But again, for this purposes, we're going to say the axis always points to what we call the North Star, Polaris, all right? Because of rotational inertia. It's in a very stable, lot of mass, keeping it in that axis. The other thing I want to teach you, in addition to the physics that was rotational inertia, is just a little bit of geometry, okay? You can tell this is the planet Earth, and you can see that glare right there is coming from the light bulb that I have right next to the camera that is the sunshine. And so you can probably tell I have it in the same orientation I did before. There's our sunshine, all right? So that's what I want you to envision is where you're at, kind of right next to the sun, looking towards the planet Earth. What I'm going to talk about are photons. Let's pretend these rulers are photons, light rays coming from the sun banging into the planet Earth. The light rays that bang into the planet Earth are always parallel to each other, and they are always parallel to that plane that I described in the previous video, the plane that is the straight line connecting the Earth and the sun that we end up calling the ecliptic. All right, they're always parallel to that because the sun and the Earth are in a straight line to each other, but boy, they're awfully far apart. 93 some odd million miles, okay? So if some photons start out coming from the sun, and they start out a little bit not parallel, even the slightest bit not parallel to one another, then as they travel 93 million some odd miles, they're going to spread out to the point to where they don't bang into the planet Earth. So any photon that does bang into the planet Earth is parallel to the ecliptic, parallel to that straight line connecting the two. All right, so these two are parallel. It doesn't matter if it hits the equator, if it hits the Arctic Circle, the Antarctic Circle. They will always bang into it at an angle that is parallel to the ecliptic. Okay, so sometimes those photons in certain regions hit very, very perpendicularly to the planet. That's when it's going to get awfully warm. Sometimes those photons hit an orientation that is very, very not perpendicular to the location on the planet where it bangs into them. That's when it's going to be awfully darn chilly. Okay? And so what we're in right now is one of the 365 days out of the year. As this Earth rotates, remember, from up above, it's going to look like it goes counterclockwise. So as the Earth is revolving around the sun, okay, it's going to be going in this direction while it rotates like crazy this way. All right, so hopefully you can tell that. Now I'm going to put her back. Boom. I put it in this orientation on purpose because the North Pole is pointing that way. I'm going to keep it that way throughout this demonstration. What I want you to then visualize is where the boundary between light and dark is, the boundary between daytime and nighttime. Okay, I got half the Earth lit up right here, and I'm going to show you what it looks like when viewed from above the North Pole. Can you tell that it's not perfect in this particular demo, but it's ish? That what I have is basically the line of demarcation between day and night goes right through the North Pole. All right, it just does. So if it goes right through the North Pole, then the folks on this part of the Earth are getting sunrise, and they got 12 hours of sunshine. Then they get sunset right there. Now we got 12 hours of dark. Yeah, that's probably a better shot of it. Okay, 12 hours of dark. Now we have 12 hours of light. And it doesn't matter if you're up close to the North Pole or if you're down here. That's Florida right there. They're getting sunrise. They're in 12 hours of sunshine. Boom. Then they're getting sunset, 12 hours of darkness. So they're getting equal amounts. And again, that won't matter. If you're in the southern hemisphere even, you're going to get 12 hours of sunshine. Go across there. Boom. Now you're going to get 12 hours of darkness on the other side. So when the line that separates daytime and nighttime goes right through the North and South Pole, that is when you have equal amounts of sunlight and darkness across the planet Earth. You'll have 12 hours of daylight, 12 hours of darkness. Everything's equal, so that's called an equinox. You know, there are two. They're called a vernal and an autumnal, and they are named from the perspective of the northern hemisphere. So vernal is what they're using to represent a springtime. Autumnal is what they use to represent, obviously, the start of autumn. So what this is going to end up being is one of those two equinoxes. Maybe you can reason your way to tell if this is representative of a spring or of a autumn equinox. But what I want you to then remember to answer that question is, this then is an equinox that represents 12 and 12. Well, I told you the Earth is going to be orbiting that way. And if I'm going to orbit that way, but keep the North Pole consistently pointing in that direction, then maybe you can tell as I go through this, and I will rotate the camera here, as I go through and keep the axis pointing in the direction that I was referencing. Can you tell now that the side of the Earth that is pointing towards the sun here is, let me get this here, is in line with it right there. And can you tell what continent is there? This is North America. So if the North American continent is in line with the sun, or very, very close to it, If those light rays are very, very close to direct, meaning this is where the sun is hitting and it's very, very perpendicular to the folks there in Mexico, it's hitting very perpendicular. But to the folks down in South America, you can tell that's very not perpendicular to the surface. But up here it is. So in the northern hemisphere, we're getting very direct or perpendicular rays of sunshine. That means it's summertime up here. This is the first day of summer. This is the summer solstice, which means when I was going back in time, or when I started